In this video, we will be presenting our work Neural Data Server, a large-scale search engine for transfer learning data. Transfer learning has proven to be a successful technique to train deep learning models in domains where little training data is available. A common practice today is to pre-train a model on a large generic dataset, like ImageNet, and then fine-tune its weights on the target domain. On the other hand, we have seen an increasing scale of available datasets, and the sizes of these datasets are also significantly increasing. For example, OpenImages is 20 times larger compared to its predecessor Coco. The video benchmark YouTube AM is 1.5 terabytes in size. The computational resources required to pre-train all these massive data is clearly very expensive. Moreover, recent works have also shown that it's not necessarily the case that using more pre-training data will improve the performance of downstream tasks. So a problem we face is how do we know which data to use for pre-training? Can we have something like a search engine to find the most useful data? We explored this in our work. Given a particular small target dataset, we would like to find a relevant subset of data for better pre-training. We consider a client-server setting to model this problem. A client is the target domain, an end user with a small dataset, and it wants to obtain a budget-constrained amount of data to use to pre-train its model. A data server has access to massive source datasets and aims to suggest the most relevant samples to a client. Having this client-server model implies the privacy-preserving nature, where the data server does not have access to the client's data. And we also want to minimize online computation, allowing the data server to serve many clients in parallel. We present Neural Data Server, a framework allowing clients to fetch a subset of transfer learning data that is most useful to its own target domains. Our data server indexes large-scale image datasets by representing them with a mixture of experts model. First, the expert networks are downloaded by the clients. Next, clients feed their own small datasets to these experts. This computes performances on the client's data, which are sent back to the server to communicate the relevance of the experts. Finally, the server uses this information to determine the most relevant transfer data subset. On the data server side, we define a gating function that partitions the dataset into mutually exclusive subsets and train one expert per subset. These experts are trained offline on self-supervised tasks, where we use the task of predicting image rotation. The experts are hosted on the data server and sent to each client. Next, the experts' accuracies on self-supervised tasks is computed on the client's dataset. These accuracies are used as a proxy to determine the importance of the server's data samples. After the client sends the transfer performance to the data server, the server performs sampling according to the importance weighting of the data points and constructs the final list of data samples to the client. Here, we show for each client dataset samples of images recommended by our NDS. We use the union of Coco and OpenImages as our data server and consider different client scenarios. Autonomous driving domain using the Cityscapes dataset, fashion domain using the ModaNet dataset, and general scenes using Pascal dataset. Note how samples from recommended subsets are visually related to the client's dataset. Here, we evaluate an object detection task. We compare the average precision score of models fine-tuned from ImageNet initialization, models pre-trained on uniformly sampled subsets of data, and models pre-trained on data sampled via our approach. We see that for all budgets of data, using our NDS sample subsets outperforms the baseline. Here, we evaluate an instant segmentation task on the Cityscapes dataset. Our approach is 2 to 3% better than the uniform sampling baseline. We also see that pre-training with 40% or 50% of images from Coco yields comparable or better performance than pre-training using the entire dataset. We also perform a set of experiments with several classification datasets. For instance, we analyze how performance of proxy tasks reflects domain confusion measured by a domain classifier network, ablation experiments on different choices of gating function and expert training. We compare with data selection methods like KNN and importance sampling, as well as analysis of the required training time of the server as new datasets is being incrementally added to it. In summary, we propose a framework for finding transfer learning data. Our framework is implemented as a web service for client applications to find data for pre-training, and we invite everyone to check it out.